Welcome to the Team Hedef's 2018 Flight Readiness Review. In the following next 10 minutes, we will introduce our unmanned aircraft system named Tulpar. Team Hedef consists of 21 engineering students from various disciplines such as aeronautics and astronautics, electronics and communication, and mechanical engineering. 15 new members joined the team this year. In 2017, Tulpar was designed from scratch, and this year, detailed optimizations in the design are done. Tulpar can carry payloads up to 2 kg, while the maximum takeoff weight is kept in the limit of 6.9 kg. Tulpar is capable of autonomous flight up to 15 minutes with an operational range of more than 10 km. In order to reduce the weight of the tail, new tail without horizontal tab is designed while providing a stable flight in 3 directions. Fuselage size is optimized according to the required volume by the interior systems, and narrowed fuselage provides less drag and weight. Nose design is enhanced to have smaller cross-section area to have fewer drag thanks to smaller sized camera selection. Flaps are used to keep the takeoff and landing distance less than 25 meters, and also touchdown speed of the aircraft is decreased. Tulpar consists of 5 main components: wingset, inverted V-tail, tail connection booms, fuselage, and fuselage hatch. The design had to be detachable as far as transportation to competition field and test flight airfield is concerned, and also it is beneficial in terms of maintenance of the UAS. Tulpar's subsystems are introduced in 3 sections. First one is the flight control system. Pixhawk 2 autopilot module handles the autonomous operation and is programmed and tuned by Team Hedef. It receives ground control commands via the RFD telemetry link. In addition to onboard sensors in Pixhawk, airspeed sensor, GPS, and LiDAR are used. The autonomous operation is managed at the ground control station with mission planner and also a custom graphic user interface developed by Team Hedef. The manual control of the UAS can be done using the 2.4 GHz radio receiver. Second subsystem is the payload release system. Payload releasing mechanism consists of 2 servos, and each payload unit is secured with a metal rod. Payloads are inserted in a package consist of dampening material to ensure that they are delivered to the location without any leakage. The final one is the imagery system. The imagery system is positioned in the nose section for a maximum point of view for the reconnaissance mission. Instead of last year's Sony a6000 camera, a new USB 3.0 high-resolution camera that is developed by the imaging source is selected due to its reduced size and weight, while providing high-resolution images from a flight altitude of 25 meters. A custom-designed gimbal is used to stabilize the camera in 2 axes with brushless DC motors. Onboard computer is responsible for onboard image processing, which provides short reporting time to the ground station. Bullet M5 connects the UAS to the ground station via a Wi-Fi link at 5 GHz. Tulpar can operate payload delivery and reconnaissance missions autonomously with the following confidence levels: autonomous takeoff, high confidence; autonomous landing, medium confidence; autonomous waypoint navigation, high confidence; payload delivery, high confidence; reconnaissance, high confidence; geolocation, medium confidence. Numerical analysis and physical tests were executed to make sure that wings are reliable in flight. Finite element analysis was executed with the loads obtained from vortex lattice method, and wing load test was executed to simulate the forces on the wings during flight and maneuvering. Payloads were placed on the wings according to a distribution obtained from vortex lattice with a maximum load of 4G. We carried out wing flow test in order to check the accuracy of the lift calculations in XFLR5. The yarns were arranged to be parallel to the direction of the flow on the wing. At a 25-degree angle of attack, we have seen that the UAS entered the stall state. The propulsion system is chosen to be brushless DC motor with 6S lithium polymer batteries. Sunny Sky's X3525 motor is selected, and its static thrust test is conducted on ground. The motor has sufficient and efficient performance with 13:6 propeller that provides 0.6 thrust-to-weight ratio. To ensure that Tulpar has consistent ground control station link in a safe range, we conducted a range test where the UAS is flown 1 km distance. The signal rate is lowered to 73% without any disconnection issue. Takeoff speed of Tulpar was set to 14 meters per second, which is 1.3 times of stall speed to provide safe maneuver. Takeoff distance is kept less than 15 meters due to high thrust-to-weight ratio. Since the landing maneuver is risky, in addition to onboard barometer sensor PIXAC 2.1, LiDAR is used to increase redundancy and accuracy of altitude determination. Autopilot software is used for the autonomous operations. Firstly, the PID parameters are tuned on the ground by investigating the test flight log data, then the detailed tuning and verification is done via telemetry data during the flight. After these tuning and validation, Team Hedef is confident to have more than 90% of waypoint accuracy, and the missions are planned using custom interface developed based on mission requirements. We performed image process mission under different light conditions with various letters to evaluate the performance of the image processing algorithm. Identification of several alphanumerics were problematic, so the algorithm is improved after test flights, and also the sunlight effects are eliminated by adaptive ISO gain, exposure, and brightness settings via OBC during flight. After all these improvements, all of the alphanumerics are read with a rate of 70% accuracy, and the geolocation error is minimized down to 8 meters. The release mechanism mounted into Tulpar and tested during test flights. We checked the flight logs for release triggering time and improved the linearized ballistic algorithm determined analytically by comparing the desired and actual payload drop locations. The team managed to deliver the payload with less than 5 meters error. Also, we have seen that our coverages for the floor packages can absorb the impact shock even on the asphalt concrete surface. Is the most prior issue for the team, and we paid attention to apply safety procedures in each step of the design, production, and test processes. Yusuf Demiroğlu has been the safety pilot of Team Hedef since the foundation of the team in 2014. He has the required equivalence of BMFA A qualification, and his BMFA membership covers the required insurance for the competition. Including previous year's flights, he has been the safety pilot of the UAS for more than 80 flights successfully. Team uses an Ultrabook with sunlight readable screen for the ground control station that is equipped with RFT telemetry link during the test flights. The UAS is equipped with multiple redundancies of communication channels with the ground control station in order to guarantee uninterrupted monitoring and data relay. All of the radio communication devices are ensured to be in compliance with respective UK regulations. RFT radio telemetry modems are backed up with the 2.4 GHz Wi-Fi link, and the flight termination sequence is programmed to initiate if both of the channels fail. A detected loss of RC transmitter signal will trigger the termination of the flight. For the flight safety, the automatic flight termination system will kick in the event of a possible power loss, geofence breach, avionics malfunction, or any disruption of the communication systems. The automatic flight termination is done by moving the control surfaces to preset positions in order to achieve a passive active gliding maneuver. Barometer, IMU, or GPS failures trigger the flight termination system for passive gliding maneuver. If a visual assessment through the ground indicates a malfunction in the operation, the safety pilot can take the control of the UAS to trigger flight termination. The manual flight termination sequence is the active gliding with IMU instruments. A body box transmitter is set and is ready for the competition safety pilot. Before every flight, the team follows the safety checklist procedure carefully, and the comments about the flight is recorded in the test flight logbook. The team conducted more than 30 test flights with Tulpar. During the flight tests, crew members are trained for operational excellence at the field, autonomous operations are tested, and the reliability of the system is examined in the air. As a result, the team is confident that all the systems are well integrated and working well, and aims to be in the top 3 in the UAS Challenge 2018.